Number 6 from the review. This is a problem for the number of permutations obeying some restrictions, and it's actually the only type of problem from chapter 6 directly. Although some of the generating function problems use some of the same setups as in earlier chapters. But this one's directly from chapter 6. It doesn't use generating functions at all. Instead, it just says find the number of, and you'll have an actual whole number answer. Number of permutations, in this case from the set of 5 to the set of 5, 1, 2, 3, 4, 5, such that 1 is not mapped to 2 or 5, 4 is not mapped to 1, 3, or 5, and 5 is not mapped to 2 or 3. So quite a few restrictions there. There's in fact 1, 2, 3, 4, 5, 6, 7 things which your permutation is not allowed to do. So the way to count them is by inclusion-exclusion, and we start by counting out the total number of permutations. That we know, 5 factorial, right? Then we subtract off the total number of permutations which break any of these rules, counting them by rule, by the union of all the permutations that break one rule, all the permutations that break the next rule, the third rule, fourth rule, fifth rule, sixth rule, or seventh rule. So there's 7 rules. So do a minus 7 times 4 factorial. And that's because as soon as you break one rule, just one, like sending 1 to 2 or 4 to 3, then there are 4 factorial ways to finish creating the permutation. After you pick one output, there's still 4 factorial ways to finish off picking the other outputs. Alright, then it gets more interesting because now we've subtracted too much, because we've subtracted 4 factorial for every single one of those rules, but there are lots of cases where you can break more than one at a time, and that's why we need to add back in all of the intersections where you break 2 rules. So this would be total. This would be breaking one rule, and then we need to add back in intersections, so that means breaking 2 rules. Alright, so 2 rules, but this is where the permutations, or the definition of what a permutation is as a function comes into play. Because it is a function, it can't send 1 to both 2 and 5. There's only one output. So we can't break 2 rules by sending 1 to 2 and 1 to 5. That just can't happen doesn't show up in the total. And it's a 1-to-1 function. So we can't, for instance, send 1 to 5 and 4 to 5. That won't happen. But we can break 2 rules a bunch of other ways. And so based on the first feature I mentioned, that it's a function, so that we can't break 2 rules in the same given the same input, we can instead count the ways of breaking 2 rules by looking at 2 inputs. So we'll look at the input 1 and the input 4. We'll look at the input 1 and the input 5, and then the input 4 and the input 5. To break 2 rules, there'll be 3 ways to do that counting by inputs. There's 3 choices of 2 inputs. So let's say phi of 1 and phi of 4 for the first possibility. And I like to draw a tree to count the number of ways of this happening. So if I break a rule about input 1, there's two ways to do that. The output might be a 2 or a 5, right? And then to break the rule of input 4, there's three ways to do that: 1, 3, or 5. Now, if that's a input 1 went to 2, I have still all three possibilities: 1, 3, or 5. But if input 1 went to 5, because of the 1-to-1 rule, I can't use the 5. I can only use 1 or 3. And that turns out to be described in terms of these little trees, that I will never be able to have the same number showing up on branches in the same path from the beginning all the way out to a leaf. That won't be allowed. There's no place where that happens here. If I had tried to put 5 as an output of 4, I would have a 5 and a 5, which is not allowed. So that means I can only see 1, 2, 3, 4, 5 possibilities so far of breaking two rules. Okay, well, that's only the 1 and the 4, but now we need to look at the 1 and the 5. Let's start off again with the possibilities for 1, and then look at the possibilities for 5. Now, I can only use the 3 right here because I can't have 2 show up twice. It's a 1-to-1 function. However, with the 5, I can use either 2 or 3. So I get 3 possible answers there. And finally, I need to check the input 4 and 5. So, and notice this is any order that you like. I just pick the order that it shows up on the problem, but it won't matter. You'll get the same answer even if you reverse the order, like do 5 first and then 4. That would be okay too. But I'm going to do 4 first. So I have three choices. You know, when you pick the first input in one of these little trees to choose among the outputs, so far there's no trouble with listing them all. So you always get to start off with the full selection, 1, 3, and 5. Then when you pick the second output, in this case, picking an output for 5, you have to watch out because you can't have the same number show up twice as an output in a path of decisions. 2 or 3. So having picked 1, I can use either 2 or 3. No problem. But having picked 3, I can only use 2. For 5, again, I can pick either of them. Alright, now I've used up all the ways of breaking 2 rules. There's 3 inputs involved, and so for breaking 2 rules, there were 3 choose 2 ways to do that, which gives me 3. 3 choose 2 equals 3. But I need to count all the leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what will be added in here is 13 times, and now I've broken 2 rules in a permutation on 5 items, so there are 3 left outputs to choose. So every time I break 2 rules, I'll actually be doing that 3 factorial ways. I'll pick the 2 outputs for the 2 rules that I break, but then I'll have to multiply that by 3 factorial for the rest of the ways of breaking those 2 rules and finishing a whole permutation. Yeah, so let's see here. Let's get my answer partitioned off a little bit. Okay. So now I've added back in too much. I need to subtract the number of ways of breaking 3 rules. So, number of ways of breaking 3 rules. Again, there's 7 rules here, but I only can break 3 if I break 1 of each input. So, the ways to break 3 rules would be to break a rule with input 1, which means that I'll make it output 2 or 5. Then I'll break a rule with input 4, which means 1, 3, or 5. Then this, I've already done some of this work when I broke just an input 1 and an input 4. Best not look at it, double check myself. When I break the input 4 now, it would be okay to do 1, 3, or 5. If I had an output of 2 for a P of 1, but I can't use the 5 again here, so just 1 or 3. But now I'm breaking a third rule, and I have to move to input of 5. And the way to break it is to pick a 2 or a 3. So I'll have to look back and see what I've already used. If I'm here, I've already used the output 2, so I can't use it again. But I can use a 3. Here I've used 2 and 3. That means that my options have disappeared. I'll just put a little X there to show that that branch can't continue. If I break a rule with input 1 as 2 and input 4 as 3, then there's no way to break a third rule. This one has 2 and 5, so I'm looking at input 5 here. I can finish this one with a 3 as well, but not a 2, since it already has a 2 at the beginning. Now on these I have, let's see, 5 and 1. That means I can have either a 2 or a 3. And 5 and 3, I can only have 2 as the output for input 5. So, since there were only 3 inputs to start with, then this is the total number of ways to break 3 rules. And I get 1, 2, 3, 4, 5. So minus 5. And if I'm breaking 3 rules, I have 2 factorial ways to finish each of those permutations. It's just 2, but it sees a nice pattern that every time you break more rules, breaking no rules, 5 factorial, 1 rule, 4 factorial, and so on. Counts down, so that's nice. And now, theoretically, I could now add in the number of ways of breaking 4 rules. But since there's only 3 inputs to use, it's impossible to break 4 rules. It's a function, so you can't send an input to 2 different things. The rules only involve 3 inputs, so it's impossible to break 4 rules. Similarly, for 5 rules or 6 rules, of course, the most would be possible at 5 in this case. So that means I can stop. You stop when there is no more. You get to the point of breaking more rules than there are inputs. So you can put a plus 0, minus 0 here to show the last 2 possibilities. 4 rules or 5 rules, but neither of them have any to count.